Hello everybody, welcome to this our new video. Now this video is about GeoPandas for geospatial data processing. And so at first let's see how to install GeoPandas. You might not have already installed GeoPandas. So it's quite easy one. You need to write conda GeoPandas installation GeoPandas. You don't have to do much. You need to just copy this one, conda install channel conda forage, and you can come to conda PowerShell. And pip, oh no, you don't have to write, just paste that conda install this one, then enter. It will automatically get installed. But if it doesn't work, if there's any error, then you have to, I think, do this one. But I think you need to take appropriate actions when it's not going to work. It sometimes takes some time, sometimes it doesn't install easily. So I'm not going to talk about installation. We are just going to our notebook. All right, so at first we are just importing our necessary notebooks, sorry, libraries. We are importing GeoPandas, Matplotlib, and also folium for a bit of web-based or base map. Well, then run it, and now we are going to import our data actually. So this data is, you don't have to download this data, it comes with GeoPandas. So just write this one, GeoPandas read file, GeoPandas datasets, and this natural earth lowers. All right, run. You can also import your shape file as well. You need to do, what you need to do is that GeoPandas dot, I think, read file, then you need to give path dot shp file name, shape file, and you will find that's like this one, this data frame. So it's a data frame actually. Here you can see we have population and we have continent. It's a world map actually, continent, Oceania, Africa, and also different names, codes, and this geometry column. Geometry, we have multi-polygon, polygon. We'll see why some things are multi-polygon, some of these are only just polygon. Well, now the difference between this geo dataset and normal pandas data frame is this geometry column actually. Now you're going to see the data structure. Before I do that, whenever you say, let's say, countries dot plot, let's see what happens. You see the whole world comes in front of us. Why is that? Because whenever we run countries.plot, this geometry column is going to be plotted. We'll talk about that more, I think. Now let's see the data structure. What's the type of these countries? Type. It's a GeoPandas GeoDataFrame. But if there's no geometry column, it will be normal data frame, pandas data frame. All right. Now what about a column? Let's say countries dot name. Is there a name thing? Yeah, name. Normally it should be series. Now this time it's also a series, but it's geo series. That's the difference. So pretty similar to pandas. If you're already familiar with pandas, then it will be a lot easier for you to work with GeoPandas, I think. Yeah. Now type of this one. Now let's see countries dot geometry. We have all those geometries. Well, some are multi-polygon, some are polygon. We'll see that. Now if you want to just extract, or you want to see just first polygon, you can do that. 0, This is our first polygon. I think this one very small. Let's set number 10. Yeah, whatever in the index number 10. Here, let's see, 4. 4 is North America. So that should be 3. 4, yeah, 4. Yeah, North America. So this is our geometry column. Then now we are going to see why some things are multi, some things are only polygon. Here you can see that this Africa, North America, Sahara, this one, Sahara, it's polygon. On the other hand, North America, Canada, it's multi-polygon. Now let's see why Canada is multi-polygon. On the other hand, Sahara is only polygon. Now to see that, we are going to do uncomment this one. Yeah. So what we're doing here is that, right, countries.loc, countries name, we are just filtering our data by Sahara and plotting it. Let's plot it out. You see, Sahara, I think I need to change this DPI. Actually, shouldn't set this by default DPI. Now figures are getting bigger and bigger. Still, I think I need to restart it to get rid of that cause it's already called. Fine. So this is Sahara. Now you see there's no boundary, just one single shapefile. No boundaries. It's all dissolved. But what if we change it to Canada? Name, name equal. Now you see it's a multi-polygon. Why is that? Because this is a single polygon. This is another polygon, and this is another polygon. There's multiple polygons. That's why it's a multi-polygon. Alright, now let's see how can we visualize it on a base map. Now to do that, we are going to import our folium and adding a map. Dot map. This is a tile. You'll see what is this actually tiles. And we are giving it as terrain map. You can also provide Google Earth map. Let's run it. Now you see what we have done is GeoJSON. We are converting our country's data, country's shapefile into GeoJSON. That's it, and adding it to our map M. Now you see all of our shapefiles, boundaries are added. But it's not interactive. When we click on something, we don't see the data. I think we can do that. For that, we need to make separate video on actually folium. So I'm not going to do that. We're focusing on GeoPandas. Now there are a lot of base map available in folium. You see state map, terrain map, Google Maps, Google Satellite Map. If I run that, you can show anyone among these base maps. What you need to do is just change the name here. It's Google Satellite Hybrid. Now if you want SV satellite, you need to write SV satellite here. So now we are showing Google Satellite Hybrid map. You see it's a Google map, satellite map. Everything you can do in Google Earth Pro, it's quite similar. Now you can do some other cool stuff using folium actually. Let's say for example you want to measure the distance between two points, or you want to draw a polygon of points. You can do that very easily using folium. Now let's say how to do that. All you need to do is write these codes and run it. I'm not going to explain these things. It seems like I did it double. Well, whatever it is, let's say for example you want to create a new measurement. So now I want to see the distance between from here to here. You see, it's 151 miles. Also, you can you can measure the area of a polygon. You see the measure, it's 419 miles. You can add some points. Oh, it's my location actually. This one automatically it will take you to your location. You can add some lines, add a rectangle, a point. Every time you need to click on that. Actually, I did something wrong here. Why is everything double? I don't know. Something happened. Now let's go ahead and import a point shape file. Actually, it's also within this GeoPandas. It comes with GeoPandas library as well. So here you can see we have name, we have point geometry. It's these are some points. These are not polygons. So let's plot them. Plot it. You can see this is actually these are the cities, world major cities, points of major cities. And now we are going to plot our countries and also points at the same time. So here this is our countries dot plot, and we are storing it in this ax variable. Now we are going to plot cities dot plot. We are passing x is equal this ax variable, so that both of the maps are going to be on the same axis, and we are changing some colors. That's it. Now you see all the points on our shapefile, country shapefile. Now let's see that if we plot those points on folium, how will it? Here you can see we did that for our countries shapefile. Now we are going to do that for cities. That is points. Folium point. Let's run it. Oh, now it's countries to GeoJSON. Now we are going to do cities to JSON. CITIES. Alright, now you can see all the points are on folium base map. Now you can change this base map as well. We have this statement array. We can do that to statement stamen, I think. Now see, black and white. It's good for water body detection, I think. Yeah. So now let's say, for example, we have notice here that we have geometry column, but we don't have lat long columns. Now, for example, you need latitude and longitudes. How do we extract latitude and longitude from this geometry column? But there's very easy way to do that, and this is countries, not its cities. CITIES cities dot geometry dot x. So this is going to be our longitude. And then let's see actually. You see, all the longitudes are now here. 12, 9, 6. Where is that? Yeah, 12, 9, 6. Similarly, for latitude, lat equal you can do y, and we can store these variables in our data frame also. So what you need to do is cities, then in square bracket we are going to add these things. Similarly, cities. Yep. Now let's see our data frame. Oops, CITI. Yes, it is. Yeah. Now you see we have now new two columns. So there's longitude, another is latitude. Now this longitude and latitude can be plotted by using Plotly library. So what you need to do is import plotly.express, as I am importing it as px. So now we are making a figure. So px.scatter map box, it's going to be map box plot. So this is our data cities, and let long, that is let long is 0, and g hover name hover when this means whenever we hover over our mouse on our map, this name variable will show up, all the names like Vatican City, da, 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 da. Well, our data, we don't have actually much data to plot, but we'll see some in future. We'll see like we have some data, we want to plot that. I mean, whenever we hover over our mouse on our map, we'll see a bunch of data. And let's see color. Now, if you have two columns with same names, you will have 2 points with similar color. In this case, we don't have no duplicates, so you'll see that every point will be different color. Will have different color. Well, size, we don't have any size column. We'll see that actually how to tweak this size parameter. Let's run it. And you can see here also we are using this terrain based map. You can also change it if you want to. Now it's taking a bit of time. Now you see our points are popping up. The points are pretty small. We need to make it big. Let's say this one. When we hover over our mouse on that point, you can see the name of that point or place, city. I mean city. Yeah. Name, also latitude and longitude. We don't have much data, so there's nothing to show. Nothing much to show. Now, how can I increase the size of those points? Now, to increase the size of those points, we are now going to add another column named size. So let's say, for example, cities dot size, or you can change the name is it. This is going to be a new column. It's going to be range. We have 202 rows. So we are going to do that from 1 to 2023. We are not going to do that from 0, because 0 size, it's going to disappear from that point. So we are going to do that from 1 to 2003, and hopefully it will work. Yeah, there's some problem. Length 2022. Oh, 203. Now fine. Let's see cities. Yeah, now we have new column, that is with now 202, 201. These are the high size. So we can also do a bit of what? Let's divide that by 2. Divided by 2. Yeah. Now you'd see, let's run it again and add this size parameter, and now we have the variable name is z. Let's see that. Now you see our points are now bigger. It's looking good compared to the previous one. Now, so far we have used some ready-made data. Now, we haven't used any of our own data sets. Now, we are going to see how to open a point shapefile. Sorry, not shapefile, it's a CSV file. And we don't have no geometry column associated with it. Now, let's see how to visualize that. I mean, how to visualize that long CSV file this time. Alright, so this is my data, this CSV file. Let's run it. And you see we have latitude and longitude. Fine, we have some solar panel capacity, not solar actually, energy capacity data. Here we have dropped some missing values, and let's plot it. When we plot a geodata frame, you see a map. Now this time it's not a geodata frame, so you won't see a map. You'll see just some plots for all those data, latitude, longitude, and capacity. Data which is integer, which are integer in type. Alright, so how can we convert it into a geospatial data? For that, we need to add a geometry column. But before that, using this latitude and longitude, we can still make map just like what we did here using Plotly. So let's see how can we do that using Plotly. I've already written all the things. This is our data, df without missing value. Latitude is let y, longitude is let x. So you can see latitude, longitude, our name, source energy. So we'll always see the source energy, this solar or whatever it is. Then hover data, you will see type of the energy source, capacity, color, source energy. Now if we have similar source of energy, then you'll see similar color. Whenever the source is different, you'll see different colors. I mean points with different colors. So let's run it and see what happens. Now you see, now we have a lot of data to visualize. You see here the energy source is solar, and then the capacity 700, latitude, longitude. Also you see its capacity is very high and the circle is very big, because the size parameter was passed by capacity. So if the capacity is high, then the point is going to be large. That's it. And similar points, similar source of energy is represented via similar colors. These are from all solar, you see, solar. But when you go to a different color, it's another thing. It's waste. That means I think it's anaerobic digestion type biogas, wind. So that's it. Now you can also change the color by, let's say example, if you want different colors, you can do this one, because these are all unique values. So where is color this time? Right here. Now see. Now this time you see all the points are of different colors, because the column now I have passed contains all unique values, unique names. That's why. Well, now we are going to try to convert this latitude and longitude into a geometry column. And you have seen that a geometry column contains latitude and longitude inside a tuple. I mean, they are zipped together. They're zipped together and they are type point. Fine. So how do we do that? At first we need to zip them together. So for that, at first we are going to import point from Shapely geometry because we need to convert our zipped latitude and longitude into point. Yeah. So what we are doing here is zipping both our latitude and longitude data. So let's see what it returns. It's just telling me a location, not data. It's not returning any data. So let's convert it into a list and see what happens. Now you see our data are zipped together inside a list. Now you can do other things with it. Let's say for example, Control C, Control V. Now we can write a for loop for I in zip this one. Let's return, let's print I. Sorry, unmatched. Oh. Yep, now you can see we have two data. It's our X, it's our Y. Let's say for example. So now if we store it inside X and Y, and we can print X comma Y. Now you see we have X data and Y data. And if we convert it into a point, because we need point, and this is capital P. Now you see that this is exactly what we have. Point geometry. This is X, this is Y. Inside them there is no, between them there is no comma. And the same thing here. X, Y. Inside, in between them there is no comma and it's of type point. That's what we want. Now there's a bit of clean way, or I would say a tidy way of doing the same thing. Now instead of writing a for loop, we are still going to write a for loop, but it's called list comprehension. We are going to write the whole for loop inside a list. So for X, Y in zip this is one is print, this one is the final output, print point xy, and we are going to store it inside a variable. Let's say for example geometry, and run it. Fine, we have all the XY data, and now we are going to pass this geometry into a geodata frame. Now we are going to make a new geodata frame. So for that, at first you need to specify coordinate reference system for your data. For my country, it's 43. No, it's not for my country. It's I think WGS 1984 system for 4326. Yeah, it will work for you as well. Now you're going to create a geodata frame. So GPD is what? It's actually GeoPandas. GeoPandas dot GeoDataFrame. This is our data frame what we have imported. Where is this? This one. DF without missing value. Yeah, this is our data. This is our coordinates reference system. CLS equal this one here, or you can directly pass that here. Directly pass that here instead of storing it inside a variable. Then geometry is our this geometry. You can say whatever you want. Geom, and let's print it out. Geom is now you see. Now you have geometry, new column geometry. Let's print out this time. GDF GeoDataFrame dot plot. You see, these are our points. Now you can do everything. I mean geospatial processing with this data. Well, so far so good. Now we are going to see a bit more on plotting. That's not too much, it's just a bit of visualization. So we are going to use our country's data. So what we did here is edge color blue. Now you see all the boundaries are in blue color. Now you can change also edge thickness, and if you want to make this a hollow map, like this fill color is none. I mean, you want to get rid of all those colors inside boundaries. Now you're going to do face color. Face color equal none. Yeah, now you see. Now everything inside a boundary is just nothing hollow. Then let's see another one. You can also plot a column. You see we have passed a new property, that is column countries dot population. Now if we see our data, let's see that countries. We have a column named continent population, estimated population. So we're just plotting that population estimated. Everything else is just similar. So you see. Now we don't have any legend here. We can add it, add that, and the legend equal to true. Fine. Now you see a legend as well, but we don't like this type of color bar. If you don't like it, then now we're going to do another one. Yeah. Now you see that color bar is gone, and we have those legends right here. So what we did here, let's see the code. Column countries, we just converted our population estimate into GDP estimate, GDP MD estimate, okay, and use legend true scheme quantiles. Now there are a lot of classification schemes. We'll see that shortly. And you know you have quantiles, natural breaks, then what? Equal intervals. We'll see that actually. So that's it. That's Now we can talk more about visualizations, like plotting names of each continents or each of those layered boundaries. You can plot names of each of those boundaries, names inside in the middle of those polygons as well. Now let's talk about coordinate reference system a bit. I should have talked about that earlier, but I missed that. Now let's say I want to know the area of all of those polygons. So what I did countries.area. So now you can see area of all those polygons. Now this is not accurate because we are not in a projection system. We are using coordinate. And you need to use actually I think UTM zone for your particular region of interest. So now what I'm going to do is I'm going to just filter out data for Bangladesh, my country. Here you see how you do that. Countries dot loc or like that double equal bd. So the same thing I have done here as well. Let's run it. So you see this is the information only for Bangladesh, Asia, population estimate, everything. You can plot it as well. Yep. Now, now the what I was going to say is that I'm going to change the coordinate system. By default, it was 4226. I think I forgot that. That is WGS 1984. Now we are converting that to UTM zone 45. I think that's the EPSG code for UTM 45 or 46. So you need to find out UEPSG code for your desired location. Let's see the area. Now you see it's 1033, 1,33,000 square kilometers, I think. Yeah. Okay, now let's draw a line. How do we do that? Now let's say I want to draw a line in between Belgium and Germany. So here what you can do is you can extract Belgium and Germany this way. But I'm going to use this line, this code for that. You can see a line. You need to just plot Germany, Belgium and the line at the same time. So what I have done here, I have filtered out Germany and I have squeezed our data for so that I can use that in this line string variable, in this line string object. So similarly, I have squeezed the Belgium data, and this Brussels and Berlin's actually are my point data. These are my points. At first I don't need Germany and Belgium. I need Germany and Belgium for plotting actually. But for points, this a line between 2 points, I need cities data. So I am using a city and another city, a city from Germany and another from Belgium. Then we have a line string object from Shapely. I am passing Berlin's and Brussels in that line string. Now when I see line, it's a line, you see. Now to visualize the line in a map, on a map, oh, it says Berlin, Brussels. Berlin is, isn't it? And Brussels. Yes. Now you see a nice plot in between. This is Germany and this is Belgium. This is Berlin, this is Brussels. That's it. Now let's see a bit of intersection. I think union intersection, these things are more interactive and more easy to do using ArcGIS or QGIS. But let's see what are the options of doing so in Python. So again, we are extracting two variables, that is Germany and Belgium, filtering out our data. Or if you want both of them, both of the polygons under the same variable, you can do what is that isin. So we are extracting our name column. You see, this is our name column, and we have all the country names here. So at first, what we are doing here is that at first we are accessing our name column. Then isin, we are going to get Germany and Belgium within that name column. That's pretty easy one. So you see we have data for both of the countries. Now if you plot it, you will see Germany and Belgium. Yeah. Now there's a boundary in between them, you see, because there's two polygons. Here you can see we have two geometries, two polygons. Now if you would like to dissolve the boundaries, I mean you don't want no boundary, it's just single polygon, you can also do that. You see now one polygon, and if we plot it, you'll see the similar geographical extent, you see, but no boundary here. But the problem with this dissolve parameter or method is that now you lose some data. Previously, we had two data, one for Germany, one for Belgium. Now we have only data for Germany. The data for Belgium is merged. Actually, not merged. It's gone actually. When we do merging in ArcGIS, you see that one of the data we lose data for one polygon. Okay, so this time we are storing data of the first polygon, that is Germany. Well, now if you don't like to do lose your data, you can do union. But here I am. I think I'm not going to lose one polygon. Let's run that actually. When we do a union between two polygons, let's say for example x is both. You see, I mean both of the polygons, and here we have Belgium. X and Belgium, how union? Keep geometry type. Okay, true. Fine. So now we have data for Belgium, also for Germany. You see population 1, that is for Germany, and population 2, that is the data of Belgium, name to Belgium, you see. And we have two polygons as well. So here we are not losing any data, but the output is same. But no, not same. We have two polygons right now. Here. One polygon means we're losing data. If you are going to make two polygons into one polygon, then you are obviously going to lose some data. Yeah, that's pretty obvious. So we saw union. I know that my examples regarding union or intersection are going to be a bit weird or uneasy to grasp. I think it's easy in QGIS or ArcGIS. That's why I didn't put much effort on union and intersection things. So what we have done here is we have both. That is, let's say for example, that's one. Both, not both. Let's do X. Let's say for example, X is just one single polygon, and Belgium is another polygon. So now you're going to see intersection. I mean, what is common in between those two polygons. So you can see that Belgium is common. That's why we are plotting only Belgium. That's it. That's a bit on intersection union. Now let's talk about joining. Now our countries column contains a lot of variables. Now for the convenience, we are going to reduce our data into three columns. One is this one, ISO name continent. That's fine. Now let's say we want to join our countries column with our cities column. Cities data frame. So countries data frame with cities data frame. What we have common? Is there anything we have common? Yep. So I think that's one thing we have common. This ISO 83 codes, country codes. I think these are. You can see ISO 83. These are country codes. This column is common in between both of these data sets. So now we can join both of the data frames using this column. So how can I do so? You see, cities dot merge. We're using, oh sorry, actually we have made this common column artificially. Cities.iso83, you see, we didn't have any common column. So we are going to make one column that is common in between two of them. So we are making this new column ISO83, and we have assigned some common codes, country codes. Let's say for example, FI for Paris, BEL it's for Brussels, that is Belgium. So when these codes will match with the codes with this data set, then we'll have all the other columns, that is name and continent, data of countries dataset. Let's see that actually. So cities2 dot merge countries2 on, that is on which column we are going to join. Run. You see, so these are our all the data of our first dataset, that is cities. We have all this dataset already. So what we have now new is these two columns, name Y and continent Y. So for CHE, name is Belgium, sorry, Switzerland, and continent is Europe. So that's it. Now you can also plot it and do whatever you want, geospatial analysis. Well, now let's go to the last section of our video. So now you're going to see a bit of classification, that is just quantiles, natural breaks, those classifications, and you will see how to identify outliers in your data. So now you're going to load a new data set. This is for Germany. You have district median price. Median price of what? I think it's a house price or whatever it is, price. Fine. So let's plot median price. You see, it's the map of Germany, I think. Well, now we are going to use more plotting. Here you see column is median price, scheme is quantile. Fine, we saw that previously. Now you can see legend. Now here you can see 2, 4, 5. We have 5 classes. By default we have 5 classes. K equal, let's say I want 3 classes. You see, now we have 3 classes. So you can change the number of classes we can show in a map. Alright, now you're going to see all the available classifiers we have inside this map classify module. I mean those quantiles, equal interval classifiers. So now you're going to call this classifiers attribute so that we can see all the available classification or all the available methods associated in this module. So you have box plot, equal interval, Fisher, a lot of natural break, percentiles, quantiles. Well, this box plot will be handy for us to see outliers. So now let's see how does this classification classify module works. So we are creating new variable with our data of median price. Now we are going to classify our median class. What we are going to do is we are going to see equal interval. So let's run it, see what happens. So now see in between 21 to 36 price interval we have 40 counts, that is we have 40 data points. Well, out of how much total data, let's see the shape of the data, df dot shape, 130 data points. Now you can see in the second range you have 74. So most of the data are in between this range. Well, now let's see quantiles, what quantiles does. Quantile is in between, first one is the highest one. So you see, based on the classification scheme you're using, we have a lot of differences in our data. So you need to choose the right fit, I mean which one is right for your task. You need to choose that. So there's an option to, oh, now let's see YB. There's another attribute inside this variable, that is YB, bean size, I mean bean numbers, I think it's. So here 1, 4, 3, we have a total of 5 classes here, you see, from 0 to 4. So 1 means our first data is in the first classification, first class. Out of 5 classes, our first data is in the range of this one, 35 to 40. 1 means second class, 0 means first class. And our second data falls in the fifth range. That's it. So it will be handy for outlier detection. You'll see that in the next section. Now, how to find the right fit, which one is going to be right fit for our data. So you can choose that by many other ways, but there's a mathematical way that this module also provides, that is ADCM module, this attribute. So we have here quantiles, equal intervals, Fisher-Jenks, different types of classifiers. Now we are going to pass all of them inside this method, and we'll see which one has the lowest median value. So this one, that means this one has the highest fit for this data. So 1, 2, 3, 4, this one, last one. So that is Fisher-Jenks is going to be a good fit for our data comparatively. That's it. That's all this thing is suggesting, this fits. Well, now now we are going to see how to identify outliers. So now we are going to do a box plot. Inside the box plot method, we are passing a y variable, that is our data with median income. Well, now you can also see from minus infinity to 12.5 we have no data. From 12 to 35 we have 39 data, and 72 to 99 we have 4 data. That's it. So now YB shows you just the same similar thing I have said previously. So here 0 means low outlier, I mean values with low data, and 5 means high outliers. These are high values and actually extreme outliers. 4 is high whisker. 3 is Q3. Okay, fine. These are not outlier. This one is outlier, and this one is outlier. So let's see. Let's plot it. You can plot it. That's very nice opportunity. It's a bit big one. So now you can see we have high outliers in dark red color. So you can see this one is high outlier and this one is high outlier. Now let's take a look at our code, what we have done here for mapping outliers. You see we have levels. That is what we have made actually. 0 for low outlier, 1 low whisker. And what we have done here is that for B in YB we are accessing all the levels. Actually what I've done here is worth scrutinizing. So let's do a for loop. For I in YBP, let's print I. What is I? I is just these numbers 2, 4, 3. You see, 2, 4, 3. Now for 2 I want what? I want to see this one, 2Q2. So how do I do that? 2 versus 2Q2, 4 versus 5 versus high outlier. Okay. So we are going to see print level of I. Level of I means we are going to print the level at index number I, that is for first one index is 2. So we are going to print the level at index number 2. So 0, 1, 2. When index is 2, our level is 2Q2. Alright, so for 2 we are going to have 2Q2. That's how it's working. Level levels. Now you see exact matching for four hives. If you don't understand it, you need to do a bit of more analysis with it. You'll understand it after some time, I think. So that's it. I think that's all I have designed for this tutorial. Now there's a lot more you can do with pandas. I mean, in with other libraries as well. The standalone pandas power is not that much. You need to use Xarray, then cartopy library. Using those libraries, you can do a lot using Python. But other than that, what I have done so far, most of them can be done by QGIS or ArcGIS as well. There's nothing that special. But using, as I said, those libraries like Xarray and cartopy, you can do a lot more that is not possible using ArcGIS or QGIS. Maybe possible, but not easy. It would be hard for you. Okay, that's all for this video. I hope you find something useful. Thank you for watching patiently. Hope to see you in my next video.